So in this screencast, we're going to go through some examples, and we're going to talk about some more of our linear inequalities. Did you have, Sam, do you have a question?
I was just going to ask, can I move?
Yeah, absolutely. Move, get comfortable. We got plenty of room here. All right, so you see on the screen here, example 6 has two variables. It's got a y on the left and a y on the right. We want to get those two variable terms together on the same side. I typically will prefer moving my variable to the left side. So I might say in this case, hey, let's subtract 11y from the right and 11y from the left. And that's going to set me up with negative 5y on the left and 17 on the right. Now you're going to have to remember, though, that there's a small little caveat to solving inequalities. I bet Michael remembers what it is. My next step, by the way, is going to be to divide negative 5. What's that little caveat that I have to keep in mind? When you divide both sides by negative, what do you have to do? Well, the other side's going to be negative. Landon? Reverse the direction of that inequality. Notice that it was a less than or equal to symbol. Now it's a greater than or equal to symbol. Okay? And that is because we multiply or divide by a negative. So whenever you do that, switch the direction of the inequality. All right, now there's an alternate way of working this one where you really didn't have to switch the direction of the inequality. I chose to subtract 11y from both sides. What if initially we had said, well, you know what, 6y can get moved over to the right-hand side, and 17 can get moved over to the left-hand side. So in other words, if we subtract 17 from both sides, if we subtract 6y from both sides, we wind up with 5y on the right, negative 17 on the left. We divide both sides by 5, and lo and behold, I get negative 17 fifths, just like I had earlier. The inequality is a less than or equal to, and then the y right there on the right. I mean, that's the exact same answer. Look at what I've got boxed in orange. Those two answers are exactly the same. One of them is just oriented to where the variable's on the left, and the other is oriented where the variable's on the right. If I were going to graph it out on a number line, right, negative 17 fifths, I'm going to use a closed mark, and I'm going to shade to the right, regardless.
Do you want us to keep it in fraction or keep it in decimal?
Improper fraction will be preferable. Improper fraction will be preferable. So like regardless if you chose to work it the initial way in blue like I did or the secondary way in red, it's still going to be such that y is greater than or equal to that number. And then if we wanted to use interval notation, last but not least here, interval notation, remember we're going to use a bracket because it's inclusive. It's going to the right, so it'd go to positive infinity. That's that interval notation that we practiced using yesterday. Okay? So that's example 6. Let's look at example 7. And you guys, you've got a little bit of prep work at the beginning, so you guys can take a stab at it. If you're watching at home on the screencast, just pause the video, work the example, and then we'll come back and revisit it. So in this example, we've had a little bit of time to work it. And Napoleon, what was your first step? What did you choose to do?
I distribute.
Very good. Distributing and combining like terms is the name of the game here before we start moving stuff over to the other side. So minus 36 and 7p minus 28. Okay. Blake, what I said combining like terms. What'd you get to simplify that left side?
11p minus 36.
Perfect. 11p minus 36 greater than 7p minus 28. And then what do I want to do, John, to both sides now? You got a couple of choices. I'll let you roll with it.
Subtract 7p from both sides.
So we subtract 7p from both sides. Good. That means I want to add 36 to both sides. And what's that going to be? 8? Divide by 4. Do I have to reverse the direction? I don't. Jonathan, why not? Why don't I have to reverse the direction of that inequality?
Because it's not negative.
Correct. Very good. When we were dividing, like that inverse operation that we did, divide both sides by 4 to undo the multiply by 4, we're dividing by positive 4. And so, in essence, we just leave it as is. And if we graph on the number line, obviously, we're going to use the number 2. What type of mark should it be?
Open.
It should be an open mark, and it's greater than, so I should shade to the right. If I used interval notation, it'd be a parentheses, 2, comma, infinity, parentheses. All right. Not too shabby. Y'all got questions on example 6 or 7? Is this something maybe you did last year in pre-algebra, or maybe if you had algebra last year, did y'all do any of this? So some yeses and some nos. If it's new to you, I want you guys to treat these problems just like you would treat an equation. Like you and I have been practicing solving equations. Really, there's nothing different other than that one little caveat. Now, I'll take a look at this next screen that I've got right here before you. And these are some catchphrases. You don't have to write all these down, but just kind of peruse the list. And notice these are ways that we could translate from English into math. So, for example, the phrase is at least. Like if I said the amount of money in my account needs to be at least $100 in order to avoid some type of banking fee, right? Then that means as long as the amount of my money in the account is greater than or equal to 100, I'm solid, okay? So that idea of being at least or at most, we'll see these expressions in word problems, and they just need to be translated into inequalities. It's not a list to commit to memory, just a list to kind of keep in mind that these are some buzzwords or some catchphrases that will tip us off to the fact that we're dealing with an inequality. In comparison, what we've been dealing with on word problems with equalities, the word is means equals, and that's been pretty much it, right? So, this is obviously a little bit more wiggle room. So you had on the homework last night, you had some questions about the word problems. Let's start with a basic translation. Okay. So example 8 says translate and solve, graph the solution on a number line, use interval notation, still the same directions we've been following. So it says 27 less than x is at least 48. All right, for right now, I'm going to blank out the words at least. Okay. How would this translate into an equation? Okay. How would this translate into equation? Well, we'd say 27 less than x. Remember how that's the reverse order? X minus 27. And again, just think like, what's 27 less than my age? Well, it would be my age minus 27. All right, the word is would mean equals, and then 48. Structurally, that's what we're looking at here. Okay, now I'm going to, instead of blanking out that expression at least, I'm going to read it and consider, okay, the thing on the left, the expression on the left, x minus 27, is at least 48. So could it be 49? Could it be 50? Could it be 60? Of course, as long as it is at least 48. So we would say what? Greater than or equal to. It has to be at least. What if it said 27 less than x is more than 48? What would I change about my answer? Landon?
Less than or equal to.
Yeah, I would just make it strictly greater than. If instead of at least, if that expression was is more than 48 or is greater, they probably wouldn't come right out and say is greater than, because that tips tips you off to what you're using. But all right, so example 8, pretty straightforward translation. Now let's put it into application. We're going to still have to do a translation, but we'll put it into application. By the way, I didn't solve that. I just realized I forgot to solve it. But we would just add 27 to both sides. Get 75. On a number line, there's 75. We'd use an open mark and shade to the right. And interval notation, 75, comma, infinity, parentheses. Sorry, I forgot to do that part. Napoleon.
It's okay if I put 75 is less than x.
Yeah, so like conventionally, and that's a good question. If you didn't hear what he asked, he said, would it be acceptable to say 75 and then the less than symbol and then X? Conventionally, in other words, the way that we typically will see things done in a math classroom or in a math textbook is that they will put the X on the left. Okay? I'm a little bit more flexible. I don't care. I want you to be versatile enough to do it both ways, to understand that these mathematical statements are exactly the same except for the structure. They're communicating the same range of answers. Okay. Truth be told, I would, if you forced me to say which one do you prefer, I would prefer the one with the variable on the left just to match with convention, but certainly you don't have to. All right, good question, Napoleon. Other questions? All right, so let's look at this application together. It says Dawn won a grant, $4,000 to buy some stuff for her classroom. She wants to buy tablets that cost out the door $254.12. Okay, out the door just means considering all the extra stuff that they so like this might be marketed as a $200 laptop, but you're not just going to walk out the door having paid $200. You're going to have to pay $200 plus tax plus shipping, whatever. So this is out the door $254. It says, well, how many tablets could Dawn buy? Now the way that I would work this problem as a young person, somebody that's perhaps a little bit more or I guess I'll just say a little bit less experienced than you guys, would be I would just start to say, well, how much would it cost if she wanted to buy one of them? $254.12. How much would it cost if she wanted to buy two of them? It would cost $308.24. How much would it cost if she wanted to buy three of them? Wait a minute, what did I say? 300. Sorry, 500. My brain stopped working momentarily. Right, and then what would we be up to? 750. 762.36. 762.36. This is called brute force, right? ... where you would get on down. And then finally, you'd come to a number that would be what? That would be too much. It'd be more than the $4,000. Like, let's say it would be like $4,100. I know it wouldn't be that exactly, but let's say it was $4,100. And whatever that value was, it would be matched with a corresponding number of tablets. And then so you would have to draw the line above that, and you'd have to say, sorry, you can't have that many. It costs too much. You don't have enough money, right? And that's what a lot of kids do when they're young, and they're counting their coins, and they're thinking, okay, how many pieces of gum can I afford at the Mexican restaurant, right? And so this type of thought process going down the list would be brute force. It would not be very efficient, would it? So we've got algebra instead to sort of help us out, okay? What was I doing each time to get this value over here? What was I doing? I was tacking on an extra, 254. It was multiples of 254. In other words, you're multiplying the number of computers times 254.12. And what do we want to make sure that is?
Less than or equal to 4,000.
Very good, Lennon. Less than or equal to. Would it be okay if it was equal to 4,000? Of course it would. Actually, that would be ideal, because that means she's fully using all of her grant. Now, the number of tablets is what we don't know, so I could make that be my variable. I'll just do T for tablets. 254.12 less than or equal to 4,000. All right, and now, Sam, what would I do to both sides? What undoes a times by 254?
You divide it.
Good.
254.
Divide by 254.12. Divide by 254.12. Now, here we're going to get where T is approximately, this is going to be a value that we're going to need to approximate, probably using a calculator. So what value is this approximately? Have y'all run that number for me yet? All of these calculators, and y'all ain't run that number yet.
16, 18, 13. He wants to round up, but it's like 15.
I want you to just read me a number.
15.7.
15.7. Perfect. Does anybody concur with that? Okay, you guys ran that number. It's about 15.7. All right, so could she go to the store and say, hey, I want 15.7 laptops? No. She either needs to say, I want 15 laptops or 16 laptops. So which one can she afford? She can afford 15 laptops. So when we see a result like t has to be less than or equal to, let's just say 15.7, logically, we're not going to round up because she doesn't have enough money. We're going to go down. We're going to say, hey, look, that's going to have to be 15 tablets. That's the maximum number that she could afford, right? Because if she went to 16, that's like over here, if she went to 16, it'd be too much. It'd be more than 4,000. So that 15 will be the one that we would get to right there, okay? Now that's just using math to answer a question that could be solved by brute force, but the math made it solvable in a much better fashion. Now I'd like to tack on an extra question here, just since you guys are so with it. How much change would she have left over in that grant to maybe like buy some tablet covers or to buy some screen protectors or to buy whatever? What would I do there to calculate how much she's got left in her grant?
Would you multiply the number of tablets by the original price for each tablet?
Yeah, very good. So we would say, 15, and one of you guys with the calculator can do this, 15 times 254.12, what's that equal? 0.8. All right. And then we would just say, all right, well, subtract 4,000 minus that, and then this will be her change left over to buy, some screen protectors or whatever. You know what I'm saying? So like this is a real world type question that you, as a consumer, you go through and you ask yourself, well, how many of these could I afford to buy? I've got whatever my budget says, and then, hey, I want to make sure I use as much of my budget as I can use. All right, so for this screencast, I'm going to call it quits. We looked at a couple of examples of just solving some basic inequalities, and then we saw those skills being put into use here in this last example with a real-world scenario.